Here's a weird question. McDonald's used to sell chicken nuggets in boxes of 6, 9, and 20. So you can buy 6 nuggets, or 12, or 15. But some numbers are just impossible. You can't buy exactly 7 nuggets, and you can't buy 11. But what is the largest number of nuggets that you can just not get? No matter what combination of orders you make, you cannot get. I'll give you a second to try to think about this one. The answer is 43. Because after 43, you can order any number of nuggets you want, forever, to infinity. But 43 itself, you just can't. No combination of 6, 9, or 20 will ever create 43. And behind this number is a question mathematicians struggle with to this day. So, let's build this equation from scratch. So, to simplify this, imagine 2 boxes, one of 3 nuggets and one of 5 nuggets. Just because 3 boxes is messy, it's less simple and it's way easier to make a formula for 2. So let's start with that. Imagine the 2 sizes, 3 and 5. What totals can we make? And let's plot this on a number line. Obviously, we can get 3 nuggets. We can get 5. 2 3s, that's 6. 3 and 5 is 8. 3 3s is 9. 2 5s is 10. 6 and 5 is 11. 6 and 6 is 12. 8 and 5 is 13. And so on and so forth. But let's focus on the gaps here. The ones that we cannot make. For instance, 1, 2, 4, and 7. But after 7, it just stops. Because after 7, every single number is reachable with 3 and 5 forever. So here's why it stops. This is the key idea. And this is one of the most important ideas in the entire video, so please, watch closely. Let's look back at our number line for a second. These 3 numbers stand out to me. 8, 9, and 10. But why do they stand out? Well, there are 3 natural whole numbers that are real that line in unison together. Now keep in mind, the size of our smallest box is 3. So let's add 3 to 8. 8 plus 3 is 11, the number after 10. 9 plus 3 is 12, the number after 11. 10 plus 3 is 13, the number after 12. And now if we take 3 plus 11, we get 14, the number after 13. And the chain repeats forever, indefinitely. So the moment that you can make a consecutive run of numbers that is as long as the smallest box, you've reached your chain. And you can make any number beyond it. So now our question lies. Instead of finding the largest number we cannot make, what is the smallest number that results in a chain? A chain whose length is the exact same size as our smallest box. And the number just before that chain lies our answer. So now that we recognize our pattern, we can try to make a formula for this pattern. Imagine, instead of 2 boxes, size whatever, we have 2 boxes, size A and B. Now to make this formula, all we gotta do is take A times B, and then take A and subtract it from their A times B, and take B and subtract that from A times B. For instance, 3 and 5. 3 times 5 is 15, minus 3 is 12, minus 5 is 7. And that is exactly the answer that we just found. Now let's try 2 boxes, 2 different boxes, 4 and 7. Well, the formula says that 4 times 7 is 28. 28 minus 4 is 24. 24 minus 7 is 17. And sure enough, 17 is the largest total number that you cannot build from groups of 4 and 7. If you don't believe me, go ahead, pause the video, take some time, and try to work it out. I guarantee you, no combination that you make of 4 and 7 will ever equate to 17. Our formula works. But to our magic formula, there is one catch. Coprimality. You see, this formula only works if two numbers share no common factor. To test this, watch as I put 6 and 9 into the formula. We can take out 3 from both 6 and 9. And what we'll find out is, as we go down the line, every number we can make is a multiple of 3. For instance, we can make 6, we can make 9, 6 and 6 makes 12, 6 and 9 makes 15, and 9 and 9 make 18, so on and so forth. But all of these numbers are multiples of 3, which means you will never be able to make a number that is not a multiple of 3, no matter what combination of 6 and 9 you put together. For instance, you cannot make 7, you can't make 10, you can't make 13. You just can't. So, if they share a greatest common factor, there is no largest impossible number, because there's an infinitely many amount of numbers that are impossible. So the formula, to even mean anything, has to have coprimality within your numbers. So, back to the McNuggets. No formula. The real McNuggets. 6, 9, and 20. That's 3 numbers. And this is where it gets a bit more challenging. For 3 or more numbers, that formula that we just made, the simple one, it doesn't exist. You see, the fact is, mathematicians have been searching for over a century, yet there still is no clean equation that gives our answer. But notice something. In the beginning of the video, I said the largest possible number with 6, 9, and 20 is 43. Now here is where our trick comes in. 6 and 9 are both multiples of 3, but 20 is not. That 20, that one box of 20, breaks us out of that multiple of 3 trap. And as long as the whole set does not share a common factor, just like 6, 9, and 20, there is still a largest impossible number. We just can't get it from our formula. So how do we actually find the number 43? So here's a tricky but clever trick that mathematicians use to solve for the number 43. It's called the mod 6 trick. Instead of one giant number line, like we used with 3 and 5, I want you to imagine splitting every number that's possible into 6 separate lists. We're splitting them up by the remainder that you get when you divide it by 6. Why 6? Well, 6 is their smallest box. You see, if I can get any number, I can always get that number plus 6, plus 12, plus 18. You see, if I can get to any number, all I got to do is add 6, and I know for a fact that's another possible number. So picture 6 ladders, 1 for each remainder, 0, 1, 2, 3, 4, and 5. Each one is 6 rungs apart. The instant I step onto the first step of any ladder, I can just step onto the next step that is 6 boxes away. Meaning, the question now boils down to not which ladder is the hardest to climb, but rather which ladder has the furthest first step. Because after we get to our first step, each rung, no matter what ladder we're on, will be 6 boxes away. So, what is the lowest rung I can reach using only 9s and 20s? Well, the smallest one is remainder 0. Because if I don't have a box of 9 and I don't have a box of 20, we're getting 0. 0 divided by 6 is 0, remainder 0. But what about the second smallest first step on the ladder? That one is remainder 3. Because the ladder with remainder 3, its first step is 9. We just have one box of 9 nuggets and no boxes of 20 nuggets. 9 divided by 6 is 1, remainder 3. Our third smallest jump is remainder 2 ladder with a jump of 20, because we have 0 boxes of 9 and 1 box of 20. If we take 20 divided by 6, we get 3 remainder 2. In other words, 20 mod 6 equals 2. Remainder 5. We have a box of 9 and a box of 20, which equals 29. 29 mod 6 equals 5. Remainder 4. 20 plus 20 equals 40. 40 mod 6 equals 4. That leaves with remainder 1. The furthest first step that we have to take. The smallest number that we can make with only 9s and 20s, that when divided by 6 gives us a remainder of 1, is 49. 9 plus 20 plus 20 equals 49. 49 mod 6 equals 1. Now look at all these rungs, all these ladders. 0, 9, 20, 29, 40, and 49. The biggest and the hardest ladder to step onto is 49. And that is the remainder 1 ladder. That means every remainder 1 number below 49 is impossible, and every remainder 1 number above 49 is possible, because you add 6 to 49 and get 54. 55, sorry, bad math. We get 55. And we add 6 again, we get 61. We keep on adding over and over and over. But the fact of the matter is, if we can keep on adding 6, that next number is still possible. But what if we subtract 6 from 49? Well, 49 minus 6 is 43. That's our number, 43. 43 mod 6 is still 1. But that's odd, because 49 is the lowest possible number with a remainder of 1. Yet 43 also has a remainder of 1. Because 43 is less than 49, and both numbers have a remainder of 1, and based on the rules that we previously set, 43 is now the largest impossible number that we can never make with any combination of 6, 9, and 20. And if you don't believe me, try this method for yourself, or try to make a larger impossible number. I can guarantee you can't. And there it is. No formula. All we did was split each number into 6 ladders. We found the hardest first step for the ladder, and that was the bottleneck that showed us the answer, 43. And there it is. The modular 6 method. So there it is. The whole story, from front to back. The entire story about how Chicken McNuggets can stump mathematicians to this day. You see, we take 2 box sizes, and it's an amazing, beautiful formula. A times B minus A minus B. You take 3 or more boxes, this formula disappears. But with clever tricks, mathematicians are still able to find remainders and crack the code. This problem is called the Frobenius coin problem, or, as most call it, the Chicken McNugget theorem. A simple yet challenging question that hides some secrets behind fast foods and genuinely difficult math that you can try at any time of day. You can test out, and who knows, maybe you will find a formula for 3 or more boxes. So next time you're at the drive-thru getting McNuggets, you'll know exactly which order is impossible. Pretty cool, right?